Good day everyone, I am Johnny Escobedo and today I will be going to discuss to you the problem solving that I made about the heat energy, the calorimetry, and latent heat and phase changes. Let's go! Okay guys, we are now here in our problem solving. In calculating heat energy, which is Q, specific heat can be used. The heat gained or lost by a substance is equal to the product of its mass, which is the M. Specific heat, which is the C, and the temperature change, the delta T. The formula here is the Q is equals to MC delta T. Okay, we will now proceed to our problem number 1. John Escobedo had 25 grams of copper and it takes him 235.8 joules of heat energy to heat it from 18 degrees Celsius to 58 degrees Celsius. What is the specific heat in joules per gram degree Celsius? Okay, our formula that we're going to use is the C is equals to Q over M delta T because the missing here is specific heat. C stands for the specific heat and we will be going to find it. The given here is the heat energy, which is Q is equals to 235.8 joules, as you can see in our problem here. The heat energy, the mass is 25 grams, and the delta T is the initial temperature minus the final temperature. And the answer is our delta T, which is the 40 degrees Celsius. Here we go, our solution. Putting the numbers in the equation yields, the specific heat is equals to 235.8 joules over 25 grams times the delta T. The answer here is the answer that we will be going to multiply it, and is the answer here is we'll be going to divide to our heat energy. The answer, the specific heat, which is our answer, is 0.24 joules per gram degree Celsius, which is our specific heat. Now we'll be going to proceed to the problem number 2. Dr. Strange have a gold ring with a mass of 75 grams and a temperature of 35 degrees Celsius, and it absorbs 935 joules of heat energy. What is the final temperature of the ring given its specific heat capacity of 0.27 joules per gram degree Celsius? Our formula that we're going to use is the Q is equals to MC, the final temperature minus the initial temperature, because which is our delta T, because the missing here is the final temperature and we will going to find it now. The given here is the heat energy is 935 joules, the mass is 75 grams, the specific heat is 0.27 joules per gram degree Celsius, and the initial temperature is 35 degrees Celsius. So the missing here is the final temperature. Our solution, uh, the delta T, because change in temperature, is equals to the heat energy over the mass and the specific heat. Our heat energy is 935 joules, the mass 75 grams, and the specific heat is 0.27 joules per gram degree Celsius. We will going to divide it, and then the answer is the answer here is 46 degrees Celsius. We are not yet finished because we will be going to find the final temperature. Uh, by finding the final temperature, we'll be going to derive it, change the minus the minus sign into plus sign due to derivation. So we will move the initial temperature to the delta T, so that we will find the final temperature. Here's here's the derivation. Delta T plus the initial temperature equals the final temperature. Uh, Final temperature is equal to 46 degrees Celsius because we are done finding it. Then plus 35 degrees Celsius equals to 81 degrees Celsius, our final temperature here. Now we'll be going to proceed to problem number 3. Captain Marvel was flying when she saw the bar of silver with a mass of 360 grams, and she added 1563 joules of heat energy to reach its final temperature up to 110 degrees Celsius. What is the initial temperature of the silver? Given the specific heat capacity of silver is 176 joules per grams degree Celsius. So in problem number 3, the missing here is the initial temperature, which is more likely in the problem number 2, which the missing here is final temperature. Uh, the formula is the same in the problem number 2, which is the heat energy equals to mass specific heat times the change in temperature. Given the heat energy is equals to 1563 joules. The mass is 360 grams. The specific heat is 176 joules per gram degree Celsius. The missing here is the initial temperature, which is this, and then the final temperature is 110 degrees Celsius. Our solution. Delta T is equals to QMC, which is we're going to divide it the same in the problem number 2. 1563 joules, which is the heat energy, over the 360 grams, which is our mass, and 176 joules per gram degree Celsius, which is our specific heat. We're going to cancel out the unit, which is the joules over joules, grams over grams, to so that we can come up to the degree Celsius, which is our missing here, the final temperature, the initial temperature. This is the temperature. Initial temperature is equals to final temperature minus the change in temperature, the delta T. Initial temperature is equals to 110 degrees Celsius minus 0.03 degrees Celsius. By the way, I forgot to tell you the problem number 2, the cancelling of unit, the same as problem number 3. We will going to cancel the unit here so that we can come up a degree Celsius. Then okay, we will going to subtract the 110 minus 0.03 degrees Celsius to find the initial temperature. Okay, the answer here is 109.97 degrees Celsius, which is our initial temperature here. Now we'll be going to proceed to the problem number 4 rather. Number 4. Lava girl used her lava in the titanium plate with a mass of 155,000 kg. Rises its temperature from 3,000 degrees Celsius to 5,000 degrees Celsius. how much heat energy was absorbed by the titanium plate if its specific heat is 2250 joules per kilogram degree Celsius. Our formula here is the heat energy is equals to mass times specific heat times delta T. The missing here is the heat energy. How much heat energy was absorbed by the titanium plate? Okay, given here, the missing here is the heat energy, which is the Q. The mass is equal, our mass is 155,000 rather, 155,000 kilogram. And our specific heat is 2,250 joules per kilogram degree Celsius, and our initial temperature is 3,000 degrees Celsius. The final temperature is the 5,000 degrees Celsius. The problem here is the same in the problem number 1, which is the missing here. Sorry. This is heat energy. The missing here is the heat energy. They are not the same in the problem number 1. Sorry. The heat energies that are missing here, then our solution. Heat energy is equals to 155,000 kilogram times, which is our mass, times 2,250 joules per kilogram degree Celsius, which is our specific heat, and our times the delta T, which we are going to subtract the 5,000 degrees Celsius minus 3,000 degrees Celsius to find our delta T. Q, which is the heat energy. By the way, we were going to cancel out the unit. Kilograms, degree Celsius. And 3,000, our heat energy is equals to 348,750,000 joules. Joules, because we are cancelling the unit degree Celsius, times the heat energy is equals to 348,750,000 joules per degree Celsius times 2,000 degrees Celsius, and we are going to cancel the unit so that the joules will only remain to find our heat energy, because the unit of the heat energy is the joules. Then we will going to multiply it. Then our answer here is 697 billion. So the answer here is 697 billion 500 million joules, which is the absorbed heat energy of the titanium plate. Okay, let's proceed to our problem number 5. The suit of iron mine is made of pure steel that has a specific mass and was heated with 2,345 joules, rises its temperature from 75 degrees Celsius to 95 degrees Celsius. What is the mass of the steel? The missing here is the mass of the steel. So our formula that we are going to use is the mass is equals to heat energy over specific heat times delta T. Our given specific heat is 2,345 joules. The mass is our missing part. The specific heat is equals to 460 joules per kilogram degree Celsius. The initial temperature is equals to 700. The initial temperature is equal to 75 degrees Celsius. The final temperature equals to 95 degrees Celsius. Our delta T is 20 degrees Celsius because we are going to subtract the initial temperature, the final temperature, so that we can come up this 20 degrees Celsius, which is our delta T. Solution: mass is equals to 2,345 joules over 460 joules per kilogram degree Celsius times 20 degrees Celsius. We were going to cancel out the unit, the joules, the degree Celsius, the Celsius, so that only kilogram will remain for our mass. We're going to multiply it and then divide it to our heat energy. The answer here is and the answer here is 0.25 kilogram, which is our mass. Again, now we'll be going to proceed to our calorimetry. Thank you. Okay guys, we are already done discussing our heat energy, so we're going to proceed to our calorimetry. And these are my example problem in heat loss systems. The problem number 1, problem number 2, problem number 3. And our heat gain system, here is the is here are our problem. The problem 1, the problem 2, the problem 3. So we're going to discuss first our problems in heat loss system. The problem number 1, which is finding the mass. Mr. Stephen Grant bought a piece of iron and was heated at 110 degrees Celsius and then dipped it in the container that contains 2 kg of alcohol at 28.7 degrees Celsius. The final temperature of the system is 38.3 degrees Celsius. So what is the mass of the piece of iron? The missing here is the mass of the piece of iron. First, we need to identify which of the given substances lost or gained energy and write all the given values. Our substances are iron and alcohol. Heat lost. So so how can we determine if that substances lost heat or gained heat? We can see it in our problem. Uh, the heated iron was dipped in the container that contains 2 kg of alcohol. So as we can see, the iron was heated and then dipped in the alcohol. The iron was losing heat and it will be transferred in the alcohol. So we can come up in this. We can determine which of them gained or lost heat. So our heat loss is the iron, the heat gain is alcohol. The given mass, the mass of iron is our missing piece. So we will be going to find it. The initial temperature of the iron is 110 degrees Celsius, as you can see in our problem. The final temperature of the iron is 38.3 degrees Celsius. And the specific heat of the iron is 460 joules per kilogram degrees Celsius. And our mass of the alcohol, 2 kg. The initial temperature of the alcohol is 28.7 degrees Celsius. The final temperature of the alcohol is 38.3 degrees Celsius. The specific heat of the alcohol is 2,430 joules per kilogram degrees Celsius. We will now proceed to our solution. Q lost equals to Q gained, which is the heat energy. Q, the heat energy gained. The mass of iron, specific heat of iron, the change in temperature of iron, is equals to the mass of alcohol, specific heat of alcohol, delta T. Uh, we will going to derive it so that we will we will be able to find the mass of iron. So we need to cancel out the unit that we are not going to use, which is the specific heat of iron and the delta T of iron. So we will going to derive it into this, cancel out the unit, then derive to this. As you can see, the one who remain is only the mass of iron. The mass of iron is equals to the mass of alcohol times specific heat of alcohol times the change in temperature of alcohol, which is the delta T, over the specific heat of iron and the delta T of iron. We will going to put this into our equation, the number. The mass of iron is equals to 2 kg of alcohol times 2430 joules per gram degree Celsius, the specific heat of alcohol, times 9.6 degrees Celsius, which is the delta T, over 460 joules per kilogram degree Celsius, which is our specific heat of iron, times 71.7 degrees Celsius, which is the delta T of iron. Well, we're going to solve it. The answer of this upper part is 46,656 kilogram because we're going to cancel out the unit to remain this kilogram, which is the unit of our mass. Then the answer here in the lower part is 32,982. We will going to divide it. Then we will be able to find the answer of the mass. The answer here is 1.42 kilogram, which is our mass of iron, as you can see here. Okay, we will now proceed to our problem number 2, which is finding the specific heat. In the middle of the forest, there was a miner who discovered a bar of gold with a mass of 385 grams, and he heated it at 450 degrees Celsius. And after the heating process, he dropped it in a bowl of water with a mass of 285 grams at 22.4 degrees Celsius. When thermal equilibrium is reached, the final temperature is 34.5 degrees Celsius. Calculate the specific heat capacity of the gold. So the missing here is the specific heat of the gold. We will be identifying first the given substances as the same in the problem number 1. The substances, heat lost is the gold and the heat gain is the water. Given the mass of gold is 385 grams. We will convert it into the kilograms. So here is the conversion of the grams to kilograms, 0.385 kg. The initial temperature of the gold is 450 degrees Celsius, and the final temperature of the gold is 34.5 degrees Celsius. The missing here is the specific heat of the gold. The mass of water is 285 grams. We will be convert it to kilograms here. The initial temperature of the water is equals to 22.4 degrees Celsius. The final temperature of the water is 34.5 degrees Celsius. And the specific heat of the water is 4,190 joules per kilogram degree Celsius. We will now proceed to our solution. The Q lost equals to Q gain. This step is always the same. To problem number 1. We will be derive it so that we will be able to find the missing the missing part, the mass of gold. We're going to cancel out this mass of gold, the change in temperature of gold, because the only missing here is the specific heat of gold, which is the C gold. So cancel out the mass of gold. Mass of gold here will remain because there will be no cancellation. We're going to derive it into specific gold is equals to mass of water, specific heat of water, the change in temperature of water. The mass of gold over the mass of gold times delta T of gold. Uh, Here, specific heat of gold is equals to 0.285 kilogram, which is the mass of our water, times 4,190 joules per kilogram degree Celsius, which is the specific heat of water, times 12.1 degrees Celsius, which is the delta T of water, over 0.385 kilograms, the mass of our gold, times 415.5 degrees Celsius, which is the delta T of our gold. Uh, we will uh, we will cancel out the unit so that we will be able to put a unit in our specific heat, which is the joules per gram degree Celsius. Yeah. The answer in the upper part is here, 14,449.22 joules per kilogram degree Celsius over 159.98. We will going to divide it. The answer here is 90.32 joules per kilogram degree Celsius, which is our specific heat here. Now we are done finding the specific heat in problem number 2. We are going to proceed in problem number 3, which is finding the change of temperature. Marx Victor bought a copper wire with a mass of 232.3 grams and he heated it, and then he poured it in the pitcher containing 345 grams of water up to 20 degrees Celsius to 27.8 degrees Celsius. What is the change of temperature of the copper? So the missing here is the change of temperature, which is the delta T. And then, same as problem number 1, problem number 2, we are going to find which is the one who lost heat or gained heat. It lost the copper, it gained the water, are given. The mass of copper is equals to 232.3 grams, convert it to kilograms, and then here it is. The initial temperature of copper is the missing one because we will going to find the change in temperature here. If there's no change in temperature, we are going to find the initial and final temperature so that we will be able to find in the delta T. The specific heat of the copper is 390 joules per kilogram degree Celsius. The mass of water is 345 grams, converted to kilograms. The initial temperature of the water is equals to 20 degrees Celsius. The initial temperature of the water is 27.8 degrees Celsius. The change in temperature of the water, which is the delta T, is 20 degrees Celsius minus the 27.8 degrees Celsius, which is the initial minus the final temperature, so that we can come up our change in temperature, which is the delta T here, 7.8 degrees Celsius. The specific heat of the water is 4,190 joules per kilogram degree Celsius. We're going to proceed to our solution. The Q loss equals to Q gain. The same process always. Cancel out the unit because we will only use the change in temperature of the copper because this is our missing piece, equals to water, derived to this. Change in temperature of the copper is equals to mass, specific heat, delta T of the water over mass copper, and that specific heat copper. We will put it in the equation. 0.34 kilograms times 490 joules per kilogram degree Celsius times 7.8 degrees Celsius over 0.23 0.2322 kilogram uh, times 390 joules per kilogram degree Celsius. Then cancel out the unit to remain only the degree Celsius, which is the unit of our specific heat, the change in temperature rather. Delta T copper is equals to 11,275.29 degrees Celsius over 90.60. We're going to divide it. The answer is 124.5 degrees Celsius, which is the change in temperature. This is the change of temperature, 124.5 degrees Celsius, the missing one. Now we're going to proceed to our heat gain system, which is they are more likely the same, but the one we're going to find it is the who gained heat. Example, the problem number 1, heat gain system finding the mass. They are more likely the same in our heat loss system. A piece of iron with a mass of 1.2 kg was heated at 110 degrees Celsius and then dipped in the container that contains an alcohol at 28.7 degrees Celsius. The final temperature of the system is 38.3 degrees Celsius. What is the mass of the alcohol? The problem in the heat loss system and the heat gain system is more likely the same, but here we are more focusing in the heat gain. So first we need to identify which of the given substances lost or gained energy. So the heat gain is alcohol. Why? Because as you can see here, the heated iron was dipped in the container that contains an alcohol. So the heat of the iron transfer into the alcohol, so the alcohol will gain heat. So the alcohol will gain heat. The heat loss is equals to iron, because the iron loses its heat due to the alcohol that was transferred to the alcohol. Given the mass of alcohol we're missing, the initial temperature of the alcohol is 28.7 degrees Celsius. The final temperature of the alcohol is equals to 38.3 degrees Celsius. The specific heat of the alcohol is equals to 2,430 joules per kilogram degree Celsius. The mass of iron is equals to 1.2 kilogram. The initial temperature of the iron is 110 degrees Celsius. The final temperature of the iron is 38.3 degrees Celsius. The specific heat of the iron is 460 joules per kilogram degree Celsius. Our solution, the same as in the heat loss, but Q gain equals Q loss, not the Q loss equals Q gain, because we are now in the heat gain system. So as you can see here, they are more likely the same. Cancel out. We will only remain this mass of alcohol because this is our missing part. Then equals to the mass, specific heat, the delta T of the iron over the specific heat and delta T of the alcohol. Derived to mass of alcohol is equals to the mass of iron, specific of iron, the delta T of iron over the specific heat of the alcohol and the delta T of alcohol here. So mass of alcohol is equals to 1.2 kilogram. This is the mass of iron times 460 joules per kilogram degree Celsius, which is the specific heat of the iron. Then the 71.7 degrees Celsius, the delta T of the iron. So you can see here, we will going to subtract it, the final initial temperature, so that we can come up the change in temperature, which is the delta T of iron. Here 71.7 degrees Celsius over 2430 joules per kilogram degree Celsius times 9.6 degrees Celsius here. Cancel out the unit so that we will be able to put a unit in our mass, which is the kilogram. We will going to remain the kilogram. Cancel. Then the answer of this, the iron is 39,578.4 kilogram. The answer of this lower part is 23,328. So we will going to divide it to find the mass of our alcohol. The answer here is 1.7 kilogram, which is the mass of alcohol. Okay, we will now proceed to our problem number 2, which is finding the specific heat. Heavenly Love, Ortega, the goddess of beauty, creates a small piece of silver with a mass of 0.235 kilogram at 23 degrees Celsius, and then she put it in the box that contains 2.3 kilogram of mercury at 16.4 degrees Celsius. The final temperature of the system is 18 degrees Celsius. Calculate the specific heat capacity of the mercury. So the missing here is the specific heat of the mercury. Then same, finding the given substances, which of them lost or gained energy. Heat gain mercury, heat loss silver. Given the mass of the mercury is 2.3 kilogram. Initial temperature of the mercury is 16.4 degrees Celsius. Final temperature 18 degrees Celsius. The missing here is the specific heat of the mercury. The mass of our silver is 0.235 kilogram. 0.235 kilogram. The initial temperature of the silver is 23 degrees Celsius. The final temperature is 18 degrees Celsius. Specific heat of the silver, 230 joules per kilogram degree Celsius. Solution. Same. We will only remain the missing, which is the specific heat of the mercury. Cancel out the remaining one. Then derive it to specific heat of the mercury is equals to the mass of silver, specific heat of the silver, the delta T of the silver, over the mass of the mercury and the delta T of the mercury, which is change in temperature. We're going to solve it. Multiply. Cancel out the unit. Then the answer is upper part is 270.25 joules per kilogram degree Celsius. The answer of this lower part is 3.68. Then we will going to divide this. The answer is 73.43 joules per kilogram degree Celsius, which is our specific heat of the mercury. Okay, then we will now proceed to our problem number 3, which is finding the change in temperature. John Amplius Escobedo is known to be the most handsome man in the universe. and because of his handsomeness, the people decided to make him a gold statue with a mass of 586 kilograms and was heated up to 300 degrees Celsius to 600 degrees Celsius. Then they put it in a molder containing 234 kilograms of water. What is the change of temperature of the water? Again, finding the given substances, which is the heat gain and the heat loss. Heat gain, water; heat loss, gold. Given mass of water is equals to 234 kilograms. You can see in our problem. The initial and final temperature is missing. Also, without the final and initial temperature, there are also no change in temperature of the water, because this is the reason why we have the delta T, which is the change in temperature. The specific heat of the water is 4190 joules per kilogram degree Celsius. The mass of our gold is equals to 586 kilogram. Initial temperature 300 degrees Celsius. The final temperature is 600 degrees Celsius. Delta T of the gold, 300 degrees Celsius minus the 600 degrees Celsius, which is the initial and final temperature. The answer here is our change in temperature, the 300 degrees Celsius. Specific heat of the gold is equals to 130 joules per kilogram degree Celsius. Let us proceed to our solution. Q gain, Q lost, and then same also the process. Cancel out the one that we are not going to use, because the missing here is the change in temperature of the water. Derive to change in temperature of the water is equals to the mass of gold, specific heat of gold, the change in temperature of gold, over the mass of water times the specific heat of the water. Okay, here it is. 586 kilogram times 130 joules per kilogram degree Celsius times 300 degrees Celsius, which is our specific our change in temperature of the gold, over 234 kilogram, the mass of our water, times 4190 joules per kilogram degree Celsius, the specific heat of our water. And then we will going to cancel out the unit, so that only degree Celsius will remain. And then the answer here in the upper part is 22,854,000 degrees Celsius over 980,460. We will going to divide it. The answer is 23.31 degrees Celsius, which is our change in temperature of the water. Okay, and now we're going to proceed to our latent heat and phase changes, because we are already done in our calorimetry, which is this. Okay, here we are in our latent heat and phase changes problem solving, because we are already done in our heat energy and also our calorimetry. Now I will be going to explain to you my sample problem solving in our latent heat. Okay, problem number 1. How much heat is required to convert 0.435 kilogram negative 67.5 degrees Celsius ice into 168 degrees Celsius steam? Useful information. Specific heat of ice is equals to 2090 joules per kilogram degree Celsius. The specific heat of water is equals to 4190 joules per kilogram degree Celsius. Specific heat of steam is equals to 2010 joules per kilogram degree Celsius. Heat of fusion of water, the LF, is equals to latent fusion, which is this. which equals to 33.33 times 10 to the power of 5 joules per kilogram. And then melting point of the water is equals to 0 degrees Celsius. Heat of evaporation of water, which is the latent evaporation. Latent vapor is equals to 2.26 times 10 to the power of 6 joules per kilogram. The boiling point of the water is equals to 100 degrees Celsius. Okay, keep that in mind. This solution. Uh, heating cold ice to hot steam requires 5 distinct parts. Number 1, heat is equals to heat negative 67.5 degrees Celsius of ice to 0 degrees Celsius of ice. Step part 2, melt 0 degrees Celsius solid ice into 0 degrees Celsius liquid water. 3, heat 0 degrees Celsius water to 100 degrees Celsius water. Number 4, boil 100 degrees Celsius liquid water into 100 degrees Celsius gaseous steam. 5, heat 100 degrees Celsius steam to 168 degrees Celsius steam. This is the parts that we are going to follow, because this is the 5 distinct parts of heating cold ice to hot steam. Part A. In this portion of curve, ice temperature changes from negative 67.5 degrees Celsius. Since the specific heat of ice is 2090 joules per kilogram degrees Celsius, so we can calculate the amount of energy using this equation. The equation that we are going to use for this part is the heat energy is equals to the mass times the specific heat of ice times delta T, which is the change in temperature. Given, mass is equals to 0.435 kilogram. As you can see here in our problem, this is our mass. The temperature of the ice, temperature of the steam. Where are we now? So given, specific heat of ice is 2090 joules per kilogram degree Celsius. The initial temperature of the ice is equals to negative 67.5 degrees Celsius. The final temperature is 0 degrees Celsius. To find the change in temperature, we are going to subtract the final and initial temperature is equals to 67.5 degrees Celsius, which is our change in temperature, the delta T. Our solution to our problem number 1 is equals to 0.435 kilogram times 2090 joules per kilogram degree Celsius times the change in temperature, which is the 67.5 degrees Celsius here. So we can calculate the amount of energy. Q stands for the heat energy. Heat energy is equals to the mass, the specific heat, and the change in temperature of the ice. So we will going to calculate it. The mass times the specific heat times the change in temperature is equals to 61,367.63 joules, which is our heat energy in problem number 1. Let's proceed to our problem number 2. The part 2 rather, not the problem, the part B. Because this is the process to be able to find the absorbed heat. This is the process to be able to find the heat. Okay, then let's proceed to the part B. After reaching 0 degrees Celsius of the ice water mixture remains with that temperature even if energy is being added until the ice melts to become water at 0 degrees Celsius. We can get the energy to absorb the ice melted into the water using the equation of latent heat of fusion. The latent heat of fusion. This is the equation that we are going to use. The heat energy is equals to the mass and the latent heat of fusion. Given the mass is still 435 kilogram. The latent heat of fusion, as you can see here in our information, the heat of fusion of the water is 33.33 times 10 to the power of 5 joules per kilogram. So this is our latent heat fusion. We are going to convert it to 333,000 joules per kilogram. Solution. This is heat energy part B. So the unit is 2 because this is part B. We're going to find the heat energy of part B. Is equals to 0.435 kilogram times 333,000 joules per kilogram, which is the latent heat of fusion, and then the mass of our ice. The answer here is 144,855 joules, the heat energy part B. Let's proceed to part C. Between the 0 degrees Celsius to 100 degrees Celsius, there are no changes in phase. Therefore, the energy added to the water increased its temperature. So, the energy needed to increase the temperature can be calculated using the same equation as part A. The equation we are going to use is the Q is equals to MC water delta T, because we are going to find the temperature of the water. The energy, the heat energy. Given mass is equals to 0.435 kilogram. The specific heat of the water is 4,190 joules per kilogram degrees Celsius. Initial temperature is 0 degrees Celsius. Final temperature is 100 degrees Celsius. Then our change in temperature is equals to 100 degrees Celsius, because we are going to subtract the initial and the final temperature so that we can come up with our change in temperature. Solution. Solution in our part C. Q is equals to 4.435 kilogram times 4,190 joules per kilogram degrees Celsius times 100 degree Celsius. The answer here is 182,265 joules. Cancel out the unit so that joules will only remain for our unit in our heat energy. Okay, same as in the part B and part A. Cancel out the unit. Let's proceed to our part D. At 100 degrees Celsius, change in phases occurs from liquid water to steam. In part B, the water-steam mixture remains constant, but this time at 100 degrees Celsius. Its temperature remains at 100 degrees Celsius until all liquid converts into steam or vapor. The required energy to convert 0.435 kg of water at 100 degrees Celsius of liquid to 100 degrees Celsius of steam is 983,100 joules using the equation of the latent heat of evaporation, which is this, the equation that we are going to use. Given mass is equals to 1 times 10 to the power of negative 3 kilogram. The latent heat of evaporation is equals to 2.26 times 10 to the power of 6 joules per kilogram, or 2,260,000. Solution. Q is equals to 0.435 kilogram, which is our mass, times 200 2,260,000 joules per kilogram, which is the latent heat of evaporation. We will going to multiply it, and the answer is 983,100 joules. Okay, cancel out the unit, remain only the joules for our unit in our heat energy. Let's proceed to the part E. During this portion of the curve, as of part A and part B, there are no changes phase occurs. Hence, the added energy results in an increase in stem temperature. In calculating the energy required to raise the stem temperature to 168 degrees Celsius, so we need to use this equation, which is the Q is equals to MC stem change in temperature, which is the delta T. Given mass is equals to 0.435 kilogram. The specific heat of stem is equals to 2010 joules per kilogram degree Celsius. The initial temperature is 100 degrees Celsius and the final temperature is 168 degrees Celsius. Change in temperature is equals to initial temperature minus the final temperature. Then this is our change in temperature. The 100 degrees Celsius minus 168 degrees Celsius equals to 68 degrees Celsius. Our solution. The heat energy in part E is equals to Q is equals to 0.435 kilogram times the specific heat of the stem 2010 joules kilogram degree Celsius times 68 degrees Celsius, which is the change in temperature. The answer here is 59,455.8 joules. Again, never forget to cancel out the unit. Just remain only the joules, because joules is the unit of our heat energy, which is this. Then we will now find the total heat. To find the total heat of this process, add all the individual parts together, which is this. The heat energy total is equals to heat energy number 1, part A, which is 1, plus heat energy number 2, which is the part B, plus heat energy number 3, which is the part C, heat energy number 4, which is the part D, and heat energy number 5, which is the part E, which is this. Q5, Q4, Q3, Q2, and Q1. We will be add it all so that we can find the total heat. Total heat energy is equals to 61,367.63 joules, which is the heat energy part A, plus 1,044,000 rather, plus 144,000 rather 855 joules, plus 182,265 joules, which is the answer of the heat energy number 3, plus 983,100 joules, the heat energy number 4, plus 59,455.8 joules, the heat energy number 5. Add it all, and then we'll be able to find the total heat energy, which is 1,431,043.43 joules. The heat needed to convert the 0.435 kilogram of negative 67.5 degrees Celsius ice into 168 degrees Celsius steam is this, the total heat energy, 1,431,043.43 joules. Okay, we are now done in our latent heat and phase changes. Thank you for watching. God bless.